Good. So again, thank you very much, Amy, for the opportunity to share some of the research activities that are going on in my lab over the last few years. And towards the end, I might also share a little bit about my thoughts in terms of how, related to the topic here, how AI, robotics, and cyber physical systems would contribute to agriculture now and in the future. But anyway, before getting anywhere, you might be noticing that I have a blank screen right now, and would like to start with these two pictures and give you guys 5 seconds to kind of digest those two. So, as Amy introduced, my name is Manoj Karkee, Associate Professor at the Center for Precision and Automated Agricultural Systems and Biological Systems Engineering Department at Washington State University. I've been here in the center for about 10 years now. Before joining Washington State University, I did my PhD in agricultural engineering and human-computer interactions at Iowa State University. Before that, I was a graduate student at Asian Institute of Technology in Thailand and undergraduate student in a university in Nepal. Before introducing what we do and why we do what we do, I wanted to spend a couple of minutes, maybe 2 minutes or less, about where we are. Because of this venue, most of our participants, or at least some of our participants coming from different corners of the world, I thought it is perhaps helpful if I introduce our location. US states, as we see here, these days you might be seeing these maps with different shades of colors indicating the number of coronavirus cases or COVID-19 cases. I hope everybody is doing okay with this situation, but let's forget about that for a moment and let's look at this map. Oftentimes when I present in foreign countries, I have to explain that Washington is not same as Washington, D.C., just indicating that here as well. Sometimes that has been a question for my audience, mostly from developing countries or underdeveloped countries, and mostly for a student population there. In the state of Washington, that's in the northwest corner of the United States. We call this region Oregon, Washington, and Idaho to be Pacific Northwest of the United States. We are located in the south central part of the Washington State. Center for Precision and Automated Agricultural System, CPAS, is strategically located here because most of the crops that we work with are around us. I'll introduce those in the next slide. But please note that our central campus, Washington State University Pullman campus, is about 2.5 hours east of, roughly east of our Research and Extension Center in Prosser, Washington. There are a number of different commodities that are valuable economically to the state of Washington. It is argued that there are more than 300 different commercial varieties of crops grown in Washington, and also we are big in dairy and other industries. But one most important economic crop in terms of economic values to the state of Washington is apples. We produce more than 65% of the total fresh market apples that is produced in the United States. Certainly, if we look into the larger picture, China produces 10 times more than United States, so it is still not as big of an industry as in China, for example, but Washington State has a significant portion of the crop being produced in the United States. Cherries, pears, wine grapes, dryland wheat, vegetable crops, including potatoes. And as I mentioned earlier, dairies, these are some of the important commodities for the state. With that, let's switch gear into kind of introducing a quick background in terms of why I do what I do. Some of these might be not that new pieces of pictures in a way, because next couple of slides will be just a flip through of a few pictures. May not be new to most of you, but still wanted to kind of bring those up as a kind of background for me to start talking about, again, my research program. Most of us perhaps have known that agricultural mechanization was recognized as one of the most important engineering achievements of 20th century. It's because, partly because we have developed and advanced engineering solutions for farming that have improved productivity substantially, improved fruit crop quality, have improved our ways we process and store produces. But most significantly, we have developed solutions that have reduced the farming population from about 70–80% down to less than 2% now in the United States. Is still producing much more than what we were producing, let's say, about half a century to a century ago. Why that? Because of some of these big pieces of equipment that we have been using in recent decades, including tillage machines that can plow thousands of acres of field with one machine and one operator, compared to perhaps hundreds or maybe even thousands of workers that would otherwise be necessary to do the same. Planters like these, again, covering wide acreages with these mechanized systems. Boom sprayers like these that are used in applying chemicals and other inputs to different kinds of crops. Row crop harvesters like these, combine harvesters for corn and soybean and wheat, and similar harvesters for sugarcane and other crops. All of these machines have been making those impact in our industry. In last 2 decades or so, there has been widespread adoption of guidance and auto steering technologies around the world. I think based on my kind of off the top of my head information, there's more than 60 or 70% of tractors being used currently around the world have these kinds of technologies integrated with them. However, all of these advancements have benefited primarily row crops or annual crops that are grown in various parts of the world, but its impact in specialty crops has been still limited. When I say specialty crops, I don't know how many of you are familiar with it, but in general, we are including fruit crops, vegetable crops, nuts, nursery crops, and things like that when we say specialty crops. And there is a document, I think, produced by United States Department of Agriculture that formally defines what we mean by specialty crops. But anyway, there has been limited practical adoption of advanced technologies in these crops still. For example, I started with these 2 pictures in my presentation today, but I intentionally converted one of those into black and white to kind of show them how similar they are. These two pictures were captured around 80 years apart. But as we can see in these pictures, the way we harvest fruit crops, in this case apples, have not changed a whole lot for last 80 years. We are still using ladders, climb up and down those ladders with bag full of apples. Sometimes that could be 30, 40 pounds of it, like 15 kg or more. And for that matter, ever since we knew how to build these ladders, the way we harvest apples, and for that matter, many other crops have not changed at all. And with all the advancements in artificial intelligence, robotics, computational infrastructure, decreasing cost of some of those, similar advancements in sensing, big data analytics, Internet of Things. All these technologies, in my opinion, brings us to a point where we start to see the possibility for developing machines for some of these field operations and relieving these laborious tasks, and sometimes even dangerous tasks, to these machines, and perhaps generating new jobs and employing these folks into some other areas. Anyway, that's my philosophy behind why I work in this area of automation and mechanization and robotics for specialty crops primarily. This is not just this is not just the area that I started working on just this last 5, 6, 7 years ago. There has been long research and development around the world trying to develop machines and technologies that would solve some of these challenges in specialty crop production, including harvesting, pruning, thinning, and so on. However, limited commercial success. And there are a few aspects why we don't have a widespread application or adoption of automated robotic solutions for specialty crop industry yet. They revolve around primarily the speed, accuracy, and robustness, or their lack of those features in the machines and the technology that we have developed in the past. Other aspect is produce plant damages that might be caused by these machines. Some of the robotic technologies may not suffer from that particular aspect, but from other technologies such as let's say mass harvesting of fruit crops has the potential to damage both plant and as well as produce. Cost and lack of adoption. There is this cycle of higher cost and lower adoption, and that leading to smaller economy of scale, and just making that entire process of developing and commercializing machines a challenge in specialty crop, particularly because we have small acreages of a large number of unique and different kinds of crops requiring specialized machines to perform different operations in those crops, and that again makes it challenging to achieve the economy of scale that might make economic sense for commercial adoption. And these are the challenges that I'm trying to address, at least some of those, through my research and development efforts at Washington State University. In my program at Washington State University, I have been focusing heavily on mass and robotic harvesting system for apples and cherries. I have investigated a little in the in other crops such as blueberries and even sugarcane and miscanthus and banana grass and some other crops, but in terms of harvesting. But my major efforts over the last almost a decade now has been in mass and robotic harvesting of apples and cherries. I have been exploring different types of end effectors, the devices that are actually engaging with the fruits, and different catching mechanisms, particularly when we're using mass harvesting technologies and different robotic systems, meaning integration of these component technologies into different forms of robotic systems. One of the efforts has been in automated cherry harvesting. This project was um, based off of a harvesting machine that was actually developed by a USDA scientist. Um, I think it was actually from the station where Amy works these days, but that was perhaps 90s and early 2000 when we were perhaps still in the graduate school. A researcher from West Virginia developed this big machine for cherry harvesting, and they published a number of papers around it with capabilities and limitations of this machine. And in my early year at Washington State University, we started off from where it was and added new features and revised or improved stacking mechanisms, from impact type stacking to kind of high frequency stacking, and we added a machine vision system into this entire machine to potentially operate it autonomously. And those were some of the, as we can see in this picture, we added a machine vision system to operate this machine in both daytime and nighttime, with prediction of branch locations, and those were again used in automated staking. And this is something we tried until a few years ago. Recently, I'm focusing more on apple harvesting, but anyway, this is one of the efforts. This second harvesting efforts that is going on at Washington State University is in apples. I don't know if the videos are playing or not at your end, but there are two videos right now running side by side. So on our left, we can see that we developed a few different versions of a single manipulator robotic system to pick apples. We did investigate different kinds of end effectors, different number of degrees of freedom, different inverse kinematics techniques, various, and we also researched on the optimal way fruit are harvested manually, amount of forces, amount of pressure, the hand motion that is involved in picking fruit. We analyzed many different of those human canopy fruit interaction part of it, as well as different parameters around the mechanical or robotic system. And we try to optimize this harvesting system to be more efficient and effective in picking apples. And starting about 2 years ago, we started to collaborate with a company called FF Robotics. I guess many of you have already heard about them. They are out of Israel. About 2 years ago, we applied the fund together to further develop our technologies into potentially a commercial machine, and that's what you saw on our right. That's not being played right now, but as you saw earlier, this is a full-scale machine we have developed, there are 6 arms on the left, 6 on the right. We provide the vision and intelligence part of the system to to our collaborator at Robotics. They have primarily led this mechanical, electro-hydromechanical system to perform all these operations. Anyway, we are continuing to test this machine, and we are quite happy with what we have gotten now, but there are still a few things that we're trying to improve in this big commercial scale machine. One of the things that we're trying to improve is the collision, robot canopy collision and low fruit detachment efficiency. Particularly, we are trying to aid a vision system that would identify obstacles such as trellis wires. We can see in the next slide, I think, yeah, trellis wires, branches, one fruit blocking another. And then we're also trying to improve our vision system that would not only detect and localize where fruit are. In addition to that, it would find an orientation for approaching those fruits so that we could pick those fruit more safely than not doing than just using location information. That's around our robotic apple harvesting efforts. In the last several years, I have been also developing an alternative technology called targeted second catch harvesting system to harvest apples. And I have, through my experience in this industry, I've seen there are many different kinds of canopies and many different ways or many different kind of philosophies going around in farming. Some farmers around the world try to minimize input and optimize the output. There are other philosophies where farmers try to optimize input to get as much output as possible. So depending upon what kind of farming structure, philosophies we're using, what kind of tree architecture we have, and also depending upon the varieties, whether that is a more consumer grade variety like Gala and Red Delicious versus some of the high-end varieties such as Honeycrisp and Cosmic Crisp, the newest variety that Washington State University introduced a couple of years ago. We might be able to use one technology or the other. So in my philosophy, robotic harvesting and this targeted second catch harvesting would go side by side. In this particular effort, what I'm trying to do is that developing a system that would have multiple layers of catchers that would go, each layer of catcher would go right underneath where the fruits are. In one of these designs, we can see on our top left corner, fruits are grown in a kind of horizontal layers, and that kind of lends itself well into this multi-layer catching, shaking and catching system that I'm working on. We apply right amount of energy, which includes certainly right frequency, right amplitude or stroke, and right duration of shaking, so that we can release this fruit with minimal energy, so that they stay close to where they are and they drop from a certain distance to these catching surfaces. And that has been quite promising for some of the varieties. You can see how it operates in this video. This is, there are 3 layers in this machine. It could have more layers. Anyway, with this machine, we have been able to harvest for a few varieties we have tested. We've been able to harvest more than 90% of the fruit, collect most of them into these catching surfaces, and keep about 90% of them in the marketable quality. which is really promising for this kind of mass harvesting mechanisms. We're also trying to add an automation component into it by using a machine vision system to find where branches are and automatically move that staking mechanism into the canopy, grab those branches and stake automatically. So these are some of the newest additions that are going on. But I want to make a note that manual harvesting currently causes about 4 to 6% damage in these fruit, uh, depending upon the variety. Our machine, even for the best varieties, is still causing about 10% damage, which is in the current situation may not be acceptable, but we have been improving a few things that we expect to help to get it down to maybe 8% or so, maybe even 7%. And then at that point, I think we start to see the potential of this machine. But in the future, it may be economic for even other varieties that would be damaged a little bit more, certainly based on the labor availability, labor cost, and other aspects that go with the farming. Again, we have not done the economic analysis of the entire cropping system and including harvesting technology like this yet, but we believe this is going to be one of the viable solutions in the future. Anyway, with that, I'd like to stop or pause and give an opportunity to ask questions, as Amy mentioned in the beginning.
All right, thank you, Manoj. So please write in your questions in the Q&A box, and if you're having trouble with that, you can write it in the chat. I'll also check there. So there is one question already. Give me a second. As we go back to work after the various quarantines related to COVID-19, there will likely be much hardship within the ag tech community. Do you know of any startups that need help to scale up, not just financially, but with respect to marketing and management?
A very good question. I have worked with or have known a few startups who are putting a lot of efforts into potentially commercializing robotic harvesting technologies. For example, FF Robotics, our company, collaborator. We have another company out of California called Abundant Robotics. We have Harvest Crew, a company out of Florida, trying to commercialize strawberry harvesting machines. Because I have been mostly focusing on harvesting, pruning, thinning some of these robotic operations for fruit crops and a little bit into weed control in vegetable crops. Most of these companies are still in their development field evaluation phases. Not sure if they have made any machines commercially available yet. Abundant Robotics was trying to do that last year, but I think they still faced some challenges. So I think they still mostly need help in financing and continuous support in terms of providing access to test sites and more than that, perhaps making farmers, fellow farmers and other stakeholders aware of these technologies that are coming up. I'm not, again, I have not thought very closely in terms of how this coronavirus aspect would impact them, but it is very likely that it will slow down their development to some extent, and that perhaps would impact the financing opportunities they have, or the financing situation they may have. So I would still think the financing is the biggest part of this process to bring these machines into farming. But certainly, anytime, anywhere, we could provide them kind of opportunities to test in the wider crops and wider varieties and wider locations, perhaps would be helpful.
Okay. Moving on to another question is, how robust are the targeted systems for variations in fruit size and color? Thinking about lots of different apple varieties, both now and in the future.
Very good question. I have been in this area, and a lot of you have been in this area for a long time. Um, we when I began machine vision system for orchards, particularly in detecting fruit, we were using more conventional techniques, and we're trying to use canopy cover, uniform background, and a few other things to try to improve our detection accuracies. With the deep learning approaches in recent years, I think we have been more robust than in the past. We don't use any uniform background these days. We are operating under open environment, under direct sunlight, and still able to detect most of the fruits in these newer modern orchards. I think during the harvesting season, I don't see a lot of challenges in terms of detecting and localizing fruit, whether that be green fruit or red or mixed color fruit. Certainly, as we try to count fruit early in the season, for example, during thinning season or some other growth stages, it is a little bit more challenging. But harvesting, detecting, counting, and locating fruit in harvesting season, I think, is not the biggest challenge anymore. I think we are robust enough to do that in many different varieties and different fruit size situations.
Okay, so now I have about 6 questions lined up, so that's great for this break. So if you have questions, just keep on writing them in, and then we'll grab them all at the end. Okay, so the next question is from Ohm. And this is related to Anna's question, which was the last question. So if some fruits may not be ripe at the same time, what are the chances of getting unripe fruits through a multi-layer shaking and catch harvest machine, which is the picture that's currently showing?
A very good question. I think that's the biggest challenge we are facing. I go with you in terms of our ability, the needs for an ability to difference to perform differential harvesting. I think I would also like to add that there are certain varieties that are already picked in a single pass. In that kind of situation, this machine is already shows a good potential already. For those varieties that are picked in a multiple pass fashion, we are in the next phase of our project. Actually, we submitted a SCRI grant. I don't know if any of you know about those grants. At least some of those from US, I think, know about that grant. We wrote a big grant recently with Stavros from UC Davis, trying to add this specific capability we're talking about. I think in short answer is that current machine does not have a capability to differentiate between ripe and immature fruit, but we have seen some promise that we can vary the frequency and amplitude of shaking system to potentially aid that capability for differential harvesting, but this is something we'd like to perform more research on.
The next question is from Santosh. Could you share which algorithms these machines use to detect edge or shapes of apples and their color?
Again, with the deep learning techniques, as we know, we are kind of using a black box and sending our images at the input level and getting our output as location of these apples, um, kind of end-to-end training process. And in terms of getting color, shape, and size, we could certainly add this tiny piece of post-processing after these locations are identified. There are two, or let's say, two parts of it. One, we have published a number of our papers around fruit detection and counting, they are publicly available and I can share those anytime. But then there are some aspects of recent advancement that are of proprietary nature with this FF Robotics company being the collaborator, which may take some time to be published. And I may not be able to share all of the recent advancement that happened over the last 2 years, but everything that has happened before that is already publicly available, and I can share those papers and potentially even algorithms as needed.
Okay, thank you. The next one's from Enrique. So do you think that the combination between robotic harvests and a UAV or drone for yield estimation based on computer vision can improve the results?
Not quite sure what does that mean. To some extent, if we have a good robotic picking system, it would be able to map the yield in the field. In terms of estimation before harvesting, we have been trying UAV based as well as ground based systems for a number of years. I think there are always challenges of going from what we see to what actually is there. We have been also developing handheld solutions for this, but yield estimation has still its own challenges, and certainly robotic harvesting has its own challenges, but I'm not quite sure how we're trying to integrate those together. Perhaps we can talk about it offline after the seminar or maybe in the later other venues.
Okay. The next question is about what's the current comparison between harvesting time for humans versus robotic harvesters?
A very good question. Um, if you ask an experienced young worker to pick as fast as he or she can in a half an hour, 20-minute session, you'll see at least 2 fruit per second being harvested by a human worker. But if you average commercial harvesting over 12 hours or 10-hour shift, they harvest about 30 apples per minute manually. It includes time it takes to climb the ladder, get down the ladder, move or empty the bag onto containers or bins. All of that included, on average, is about 2 seconds per apple for manual picking. The robotic systems have different kinds of philosophies. One is make your arm as fast as you can, but use a smaller number of those. Abandon Robotics claimed at some point that their Delta robot has a speed of 1 fruit a second. My own prototypes, which were not actually optimized for speed, they were developed to prove the concept of different algorithms involved, including inverse kinematics and prioritizing which fruit to pick, in addition to vision system and control systems around all of that. They were not optimized for speed, but we were able to still get to 5 seconds per fruit, something like that. With the FF Robotics amps, 12 amps in a machine, about 3 seconds, 2 to 3 seconds per fruit. We're talking about half a dozen fruit or so per second if all the amps are working together. So anyway, these are some of the numbers that go together. I think eventually it comes down to the economics of picking a piece of fruit. How much does it cost manually and how much does it cost with a machine for a piece of fruit? I don't think there is a comprehensive study already in place, but I think we have a clear indication that these machines would be able to meet or even exceed the per fruit picking cost compared to manual picking.
Then the next question is from Dave. And it's about what are the biggest technical challenges associated with deploying robotic platforms, for instance, the vision part or the handling of the fruit. So to add some clarity to this question, what would be the most important things for funding agencies to focus on?
I I think vision part has been the focus in the past 10-15 years, and I think we have achieved reasonable performance in that area. There are still a lot of challenges certainly in that space as well, but perhaps less of a bottleneck now than mostly towards I'm perhaps keeping apple harvesting as an example in my mind. We could, if we have more time, we could discuss about all aspects of robotic operations and farming. But in my opinion, there are still a lot of challenges in optimizing the robotic system and getting to the target in the lowest possible or highest possible speed and lowest possible cost. For example, in apple harvesting, how do we avoid obstacles and still be able to pick this fruit at speed and cost that would make economic sense? If it is pruning, how do we get around brands and get to the other brands that actually needs to be pruned out instead of the one that is in front of you? So these aspects are, I think, more of a challenge now than the vision system, in my opinion. Fruit handling, particularly for harvesting robots, fruit handling perhaps is not the biggest challenge, because there has been companies who have commercially used bin filling and conveying systems, I think with reasonable performance that could be tapped onto and perhaps further improved. So I think it's still the major effort in terms of research and development in the future and potential funding would be in optimizing electrohydromechanical systems for most efficient, low cost, and faster actuations.
And then this is the last question for this break, would be from Amir, is how would you compare FF robotics, multi-arm and simple arms versus abundant robotics, one parallel and fast robotic? And what do you think are the advantages and disadvantages of the two approaches?
This is the most difficult question for me. So I kind of indirectly already covered those areas.
Right, and you can choose how to answer the question because you're in
sure.
charge.
Yeah. Let me say this. I don't know if FF Robotics or Abundant Robotics folks are in this call at all or not. That shouldn't matter at all, but I still want to give them a chance if they are there to speak for themselves. I started in this area about 9 years ago. And initially we were working alone, and then I found, or I met with Kurt Salisbury, who is the CEO, CTO, I think, of Abundant Robotics now. We met, we discussed, and I kind of introduced him to potential for robotic harvesting in apples. We started working together in a conceptual level for a few years. And then at some point, I got my own funding from USDA, and he got his funding from private companies and resources, and we continued to develop these technologies in parallel. But then about 2 years ago, I started collaborating more formally with FF Robotics. So there has been some fine lines I've been walking through in terms of keeping the non-disclosure aspects of these collaborations in place. So I'm biased in a way if I say one thing or the other in terms of what works or what doesn't work. But as I said earlier, these are different philosophies. Do we want to use the simplest architecture, machine architecture use more of those and perhaps achieve the same economic value compared to a faster, more complex or perhaps more expensive piece of machine, and perhaps achieve the same commercial outcome or potentially higher, right? Again, I don't exactly know where these technologies stand in comparison to each other, but I think these are just different philosophies. Both might work as well.
Okay, wonderful. So let's let you finish the rest of your presentation, and then whoever wants to hang around and ask questions, if Manoj has time, we can. Okay, thanks.
So next part. That's not what I wanted to do. What I wanted to do is getting rid of the Q&A, and which is not allowing me to do. Anyway, I'll move on. I don't know what you see in your screen, but in my screen there is the questions that were asked are in the middle of my slide. I'm trying to get rid of that, but it doesn't matter for me. Hopefully your side is okay.
It looks fine. Yeah.
Harvesting has been the major effort, but next couple of minutes I'll quickly flip through other areas of my recent efforts. One of those has been what we call canopy and cropland management. We're looking at robotic thinning of flowers, robotic thinning of green fruit, as well as robotic pruning in different kinds of apple and cherry orchards. This quick video here shows a laboratory mock-up kind of experiment for robotic pruning. If the corona situation were not there, potentially we would be in the field by now evaluating this system in a cherry or apple orchard here in Washington, but again, we're on hold for that. And this season seems to be over now with the buds breaking already. So hoping to perform that in some other phase and potentially going to the south with our collaborators, or I don't know, or waiting next year. But anyway, this is another area of our research and development. Red raspberry cane bundling and tying has been another research efforts in my lab. I don't know how many of you know about the red raspberry crops. These crops are grown in canes. For most of the commercial varieties that are biennial bearing varieties, they require pruning of older 2-year-old canes and keeping 1-year-old canes in place and bundling, bringing them together and bundling. And that's the research project that have worked on to have this mechanism go around the canopies, bundle all the cans together and tie them together to create a sturdy, healthy canopy system for red raspberry crops. I think there is a video here that shows this machine in action. Another project we've been working on is to automate green shoot thinning in vineyards. Primary focus recently has been to locate cordons both in dormant season as well as in growing season, when these cordons are the horizontal structure of these canopies. As you can see in the top left corner, we can see the horizontal structure of these these vines very easily in the dormant season or early growth season. But as we get more growth into third and fourth week, cordons are almost completely occluded by the shoots and leaves, and we're trying to develop a machine vision system that can utilize models developed during dormant season and the canopy information, including shoot locations in the growing season, so that we can estimate trajectories of these cordons even when they are occluded by leaves and shoots. And once that is identified, we are developing a robotic system that would go around these cordons automatically to remove some of these canes as a process of green shoot thinning in vineyards. As you can see, there are these trajectories estimated based on the algorithm or the technique that I described earlier, and we're doing fairly good job. I think the actual and estimated trajectories are within a centimeter or two of each other. In terms of unmanned aerial systems of drone research in my lab, I focus mostly in what we call active applications. I don't work a lot in terms of monitoring crops and sorts, but more towards automating these platforms and doing something in the field. For example, monitoring is something too, but I kind of differentiate these applications into passive applications of sensors and things like that, and active applications of UAVs, such as applying chemicals and deterring birds and things like that. One of my areas has been to use these platforms to deter or chase away birds from wine grapes and blueberries and other crops of interest. And we have shown significant reduction in bird activities as well as fruit damage rate compared to not using any bird control solutions. Last but not the least, recently we were funded to develop a smart irrigation system with a case study in vineyards. This system would include all possible kinds of data. When I say all possible, certainly practically possible. We have hyperspectral, multispectral kind of sensing. We have soil sensors data. We have weather data. We have thermal imaging and a few other, as well as historical crop management data. We'd like to bring all of those together into a big data analytics framework and develop a decision support system that would tell us when and how much water to apply, both in space and time, and develop a irrigation system that would be able to achieve those precisions automatically. Another area of recent efforts in my lab has been to move towards individual plant level management in orchard crops, including applying nitrogen based on the needs of individual trees. And again, this is the very newest effort. We're recently funded just a month ago or so to start working in this area. This has been based on our preliminary work that shows that even leaf color during fall tell us a whole lot about the need for nitrogen, for example. In the two pictures we saw over in this slide, taken on the same day, right next to each other, we see some leaves with a lot more yellow leaves versus those who have mostly green leaves. And that is an indication of how much nitrogen they need in the next season. As we can see in the bar graph here, there is kind of a correlation between how many yellow leaves are there in a given day versus the need for nitrogen there. And that's kind of a preliminary analysis that led us to this funding, and we'll keep working in this area for next a few years. I don't know how much time we have, maybe not much, but let me spend another minute or two in terms of the direction. I believe this is the one that makes me difficult now. Oh, okay. Okay. We've been talking about smart farming for a lot, and I think we have been already looking into a few different directions in the future in terms of how we get there. In my opinion, mechanization, automation, robotics, precision management, and techniques, all these pieces combined together, with the automated decision support system that we've been working on, it will lead us to what we call this smarter intelligent agriculture. This has been and will be possible through the interaction between cyber physical systems and artificial intelligence. I'm not spending time here. I'll share these slides with you, or maybe Amy can share these slides with you. But what I try to show here is that how AI system impact a few fundamental technologies such as pattern recognition, machine vision, big data analytics, and those basic technologies would help us do a few things in farming, such as perceive plans, make farming decisions, and implement those decisions more accurately and efficiently, which then leads us to perform various tasks in farming to achieve higher yield and better quality with lower inputs. In short, more or better with less is what I believe we could do with the integration of these technologies. There are a lot of opportunities in this area, including continuous exploitation of systems approach, including artificial intelligence, cyber physical systems, IoT, big data analytics techniques, but also to include genetics and breeding. A lot of us work with geneticists or breeders to provide vision system or sensing system for them to better select their crops and things like that. I think these kinds of collaborations become even more important, and we need to continue working in this kind of collaborative environment. We have been, I think, dealing with the data versus information challenges for a long time. I think it is still a challenge. We have a lot of different kinds of data, tons of those data, and now with tons of different kinds of sensors. But I think we're still struggling to convert data into actionable information for farmers. Connectivity and interaction is a key, but I think we're still facing challenges in terms of finding fast enough of connectivity in farming areas, and I think that needs to be an area for our for development in the future. I don't know, through government or private or whoever comes into play. Big data approaches I've already mentioned. I think I'll stop around here. This is the last kind of a concept I want to introduce. Not perhaps the new concept at all, but I think farming needs to move towards this agricultural control center concept where machines are mostly operating by themselves in the field, and there's operation and supervision from remotely could occur by a smaller number of workforce working from safer and better working environment like our offices. That's kind of end of my presentation. Any questions?
Yes, we have quite a few questions. So what is your take on leveraging simulation and agricultural robotics?
Simulation, including virtual reality, I think, and augmented reality, I think, have a big role to play to speed up the prototyping cycles. I think that's true in manufacturing and other industries as well as agriculture. Simulation of interaction between machines and crop canopies is another important area. I think we need to have more research and development going on in that area. There has been some in that space already. There has been a lot of crop modeling, crop growth modeling, other aspects of crop modeling that I don't know much about, but I think those modeling and simulation efforts in crop science could perhaps be tapped into and brought into the mix of how we develop biological and engineering system together into making these systems more friendlier to each other, so that our machines operate more efficiently and effectively to perform whatever operations we're trying to perform. I think in general, there is a much bigger need of modeling and simulation, both in the physical space, biological space, as well as interaction between the two.
Okay. And then this is a question about the fruit growing systems out in Washington. So Shenglong noticed that the training system demonstrated in the video is kind of ideal. So do you think there's any strict requirements or constraints on the fruit tree training system for precision agriculture in the near future?
I think that's the most difficult question I heard. I think we need to start somewhere, and I think this is the starting point. We start with the best possible engineering solution and best possible canopy architecture that's out there, and see we can achieve what we want to achieve. When we talk about Washington State, there is a significant amount of farming already in these kinds of modern trellised fruiting wall architectures. So it is not a question I hear in Washington, because they already know the benefit of moving into those kind of architecture, not just because they want machines to work on them, but also because the productivity and labor efficiency is much higher in these modern apple orchards compared to conventional apple orchards with big 4-dimensional trees. But then it takes time for any industry to move on to those modern structures. Washington is already well into it, so it's not a big question here. But as I talk to researchers and other stakeholders, including growers around the world, this is a big challenge and larger question for them. I understand that, but I think over time, with this kind of globalization, that coronavirus also tells us how globalized we are. I think we'll learn from the best practices from other parts of the world. I think it'll be a matter of time when growers around the world would start to put this kind of architecture there, so that machine based or robotic operations become friendlier and cost effective. I cannot say it is impossible in the conventional architectures, but it is certainly much more challenging, both technologically and economically.
Yeah. Okay, then there's a lot of questions and like a start of a debate regarding shake and catch, but I think that it's revolving a bit around, so say you weren't a specialty crops person and you just saw some shake and catch machines, say for oranges or for tart cherries, and you didn't have this background of bruising or how tart cherries are processed or the ethylene release for the sweet cherry machine, for instance, all that background. Maybe could you talk about that? Like, why is shake and catch so sort of difficult and fraught for Apple?
Yeah. I should have said that second catch machines are already there and doing their job, right? In tart cherries and nuts and a lot of other fruit crops that are harvested for processing market. But for fresh market crops like fresh market apples, two aspects. One, as soon as we damage this fruit in any way, like a little bit of bruising, a little bit of cut or tear, their storability has been substantially reduced. One, and second, we consumer want a perfect piece of fruit. So given those two factors, we cannot damage not damage a big percentage of fruit during this harvesting process. Otherwise, we are throwing our production away. So in the past, we have been shaking trees, grabbing on the trunk, or we are shaking canopies with finger type or some other kinds of shakers. These kinds of shakers that have been commercially viable for crops like tart cherries, or let's say cider apples, if there are any, where a bit of damage is not a problem because they are being processed to a product that does not differentiate whether this is damaged or not. So some level of damage is okay there, but not in apple that we consume out of grocery stores. So if we take the trunk where these apples are flying everywhere, they're falling long distances, and they are hitting each other, they're being hit hard when they're caught, and that's all the things that cause a lot of damage. So in the past, it has been shown that 30 to 60 or even 70% of these fruit are damaged when we do that kind of trunk shaking or canopy shaking. And that's why I'm trying to develop this more gentler shaker that will shake a quick little branch and grab the fruit underneath, so that we have been handling these fruit gently and collecting them gently. And hopefully that leads us to commercial success in second gas harvesting. I don't know if that makes any sense, but we can talk more in other venues or via emails.
Okay, thank you. And then another question is, can you talk a little bit about, well, the question is average harvest cost per apple on manual versus machine harvested. You talk a little bit about this, but maybe a little bit more address this question.
Again, because I don't really deal with harvesting logistic at the level that I would know all the numbers. I think per box of fruit harvesting is about $20 when we talk about manual harvesting. Now I need to go back and look at the volume a box includes, but it comes down to I think 15, 20 second, or maybe 34 second, or I'm sorry, seconds, 30 cents a pound of harvesting cost for a few different kinds of varieties that are grown in Washington in these modern orchards. And if harvesting robot in the long run gets to that kind of cost, or maybe even slightly better, we have a deal. But then other aspect of it is that technology, both cost, robustness, efficiency, reliability, has a tendency to improve, whereas the cost and availability of labor is getting more and more challenging. And that's why, even if it is not breaking even now, harvesting with machines being here and manually here, there will be a time it will break even, in my opinion, fairly soon. I don't know if that makes sense, but yeah, let's stop there because of the time constraints.
Okay, thank you very much. So Manoj has his email address here, and you can also access this information from the IEEE-AGRA.com page. Thank you all for coming. Thank you so much, Manoj, for the great talk, and I'll see you next time.
Thank you, everybody. Again, thank you very much for the opportunity, and sincerely thank all of you from all around the world. I see sometimes even 45 or so participants here, even during this tough time. Thank you very much for being here, and I hopefully would get more opportunities to interact with all of you and share our experiences and learn together into the future.
Okay.